raised to 1/2 h, that's h norm, u 1/2 v norm times v 1/2 v norm v 1/2 e norm and the phi norm of h actually. Okay, so the B satisfies this inequality. So from this definition, what we can do is that we can show that B satisfies such kind of an estimate, and this would be a crucial estimate in our computations actually. Okay. So what is the third thing? The third thing is that B satisfies some properties. So the one of the property is that BU is equal to 0 for all U in V. Okay, and BU is also 0 for all U in V and W in H1. Okay, so this is it. So these are some of the properties of what do you call operator B actually. Okay. Now I'm going to do what? I'm going to record some of this information onto this. So for B, what we know that it's a map from V cross E cross H into what do you call R. Okay, where V is the domain of A 1/2, E is the domain of A, Stokes operator, and H is, we know it's a collection of square integrable divergence free vector field. And then the B of UV phi satisfies, its H norm satisfies, its absolute value satisfies this. What is this? Square root of U 1/2 H norm and V 1/2 V norm, U 1/2 V norm and V 1/2 V norm and V 1/2 E norm, okay, and H norm of the phi. Okay, so this is what is the key thing that I'm going to quote actually, and the property that BU is equal to 0 for all U in V, and BU W is 0 for all U in V and W in H1 actually. Okay, so these are the key properties that I'm going to use later on to do my computations and calculations. Okay. Let me introduce the one final last bit, and then I will be in position to put the Navier-Stokes equation in interesting form, okay, in the form that we are kind of more familiar actually, the standard form. So this map was small b. So let me define another map which is capital B. So the capital B is the map from V cross V into the dual of the B actually. Okay, so this is the map that goes like this. And how do you define this B? So you define this B as a duality. Okay, so if I take for example UV from V, then I know that my BUV is in the dual of V prime. So I'm writing a duality BUV, the duality product of BUV with a phi V prime cross V. Okay. So I want to define this duality. So what is duality? Duality of this is that, okay, you take this BUV, which is an element in V prime, and you take this phi, where the phi is from H, I guess, yes. The phi is also from V actually. Eventually everything is going to fall into H, but yes, phi is from V. And the definition of this duality is that this is equal to BUV phi. Okay? So I'm defining this duality. So what would be the outcome of this duality? The outcome of this duality is going to be, so it's defined in the terms of BU, in the terms of the small, what do you call, B actually. Okay, we know the definition of BU. Okay. Now, what can be done? Now, since this guy is bilinear, so this duality is also trilinear actually. Okay, and so this is another important thing that I must say. So what we can do next, what I can say about this B, so as I can extend a small b due to its continuity to a map to the fullest spaces, okay, from these spaces to the fullest spaces, then I can do the same with the B actually. So the B can be extended because of the continuity. B can be extended to a map B that is defined from, what do you call, V cross E into H actually. Okay, so you can define this. Next thing, there is a key property for the B that I'm interested in, okay, and that property is that if you take, say, BUU, okay, and AU, in H you're going to get 0. Okay, so BUU in a product with AU in H going to give you 0. So this is another important key property of the B is. Alright, so let me put this property here, that B is a map from V cross E into H, okay, and it's a linear and bounded. It's linear and bounded, okay, and this satisfies this interesting property, which is BUU and AU in H norm is 0 for all U in the domain A. You have to be in the domain of A so that this can make sense actually. Alright? This is what is the key thing. Now we are in position with all this stuff. So what we did so far. So I kind of wrote my Navier-Stokes equation plus initial conditions and boundary condition in case of omega when it is subset of Rn, where n is 2 is 2R3, and where the omega is full space, Rn, or the omega is the periodic domain. Okay, so I define my Navier-Stokes equation in such cases, and then I talked about what do you call the functional setting. The functional setting is different if you are considering the full space or torus. Functional setting for omega, and it is in Rn, and the omega is full space torus. And then I also define what you call this Larry-Helmholtz projection operator, and I talked about some of the properties of it. Also, what do you call define this trilinear map B and linear map capital B actually, okay, and wrote some properties of it, okay. And the key properties, all this information is basically here, okay, so it's basically here. So whenever I need to quote, I'll just quote it from here. Okay. So what is next? Now, with this functional setting that we have kind of defined, say for example, for periodic domain and for full space, you can put your equation into an interesting form actually. Okay. So consider the case when omega is the full space actually. And then Rn are full space. Okay, in this case. What was our Navier-Stokes equation? Let's remind it. Let me write it actually. So that goes like this. Partial u by partial t minus nu Laplace u plus u dot del operated onto say u plus the gradient of p equal to f, and the gradient, the divergence of u is 0 and ux0 is u naught of x. So this was my, what do you call, the first equation actually. So what I have to do in this situation, I need to, in this case, I need to apply what do you call my projection operator actually, okay, onto the entire equation. So if I'll apply my projection operator into it, so for the pi onto the both sides, so it's going to be pi of partial u by partial t is going to be, by properties of projection operator, is going to be partial u by partial t. So remember, so we had this projection operator and I wrote some of the basic properties of the projection operator, so you have to keep those properties in your head. So the projection of this is going to be this minus, not minus, but let's put, say for example, projection of minus Laplace u is going to be nu au, okay, plus projection of u dot del u, okay, plus projection of gradient of p plus the projection of what you call f actually. Okay, this is what that you're gonna get. Now partial u by partial t plus au plus what would be projection of this plus projection of pi p and projection of f. Projection of this gradient of p is obviously going to be 0 by what do you call the properties of and by the properties of Larry-Helmholtz projection operator actually. Okay, so if I now define say a map BUV, okay, I'm going to identify it actually. So let me denote an expression BUV that goes like pi of u dot gradient operated onto V. Okay, so let me define my BUV as the projection of u dot gradient onto what do you call V. Okay, so this BUV is basically one of the manifestation. It's one of the manifestation of the B that we defined previously. Okay, so it's just one manifestation of it actually. So here I have pi of u dot du. So I can say that basically the B of uu is going to be the pi of u dot del u actually. Okay, so this guy can be written as B of uu plus 0 and pi of f. So let's denote the pi of f by, I don't know, maybe some f star or something like that, or maybe we denote it again by what do you call f. Okay, so you got the equation in this form. So even if I wish, I can write this B of uu as simply B of u actually. Okay, let's denote this B of uu as B of u, and I can write this equation in this form, which is B of u equal to f. So now you can see that like this equation looks like in a more familiar form. So I have partial u by partial t, a linear operator, a nonlinearity in u, and a forcing factor actually. So it's in a kind of a form of evolution equation that we have seen already. Okay, so we have seen it already. So this is not something, what do you call u actually. All right. So similarly, so one thing that as I can write my Navier-Stokes equation in my standard nonlinear evolution equation with the linear operator form, so in such a form, you can also write this equation in what do you call in the form of in such a form in case when your omega is periodic actually. Okay, so you can also write it in this form, and think for yourself actually that how you can put and write this Navier-Stokes equation in such kind of a form when your omega is a periodic domain actually. Okay, so I'm not getting into it, so just do it for yourself. So what is the key point next? The key point next is that the problem that we're gonna attack actually is going to be this. Actually with such a conditions. Is going to be this with such a condition. Okay. Some part of this problem, and specifically I'm going to attack the problem in 2 dimension. Okay. I'm going to attack this problem in 2 dimension actually, not in 3 dimension. 3 dimension at least existence is going to be something for you. Okay. So it's something that this is something that you have to do it for yourself. Alright, so let me put also this. So the equation, the version of Navier-Stokes equation that we are interested in, the abstract version is this, partial u by partial t. For the sake of simplicity, I can put nu equal to 1 actually, so I'm going to get, say, au plus b of u, okay, and equal to, what do you call, f, and the gradient of u is 0, and u of 0x is really, what do you call, u naught of x. So this is really the star problem that I am interested in solving it for n equal to 2 case actually, when the dimension is 2. Okay, I'm going to do the existence, uniqueness of the weak solutions. Okay, so weak solutions for this problem in 2 dimension. And in 3 dimension, you know, this problem is $1 million problem actually. Okay, its existence and uniqueness is $1 million problem. So we have basically the existence of weak solution for this problem in case the n equal to 3. The real trouble is uniqueness. We don't have uniqueness for this problem, uniqueness of the weak solution for this problem in n equal to 3 actually. So this is what the major glitch is. So I'm going to do this in, what do you call, the 2 dimension.